Hi, I am Abdur Rahim, a data scientist at Royal Cyber. Fine-tuning has become a buzzword since the release of LLMs, and today we will discuss what is fine-tuning, why we need fine-tuning, and how we do fine-tuning using different techniques. Imagine you have a huge box of Lego bricks and you can build anything with them, but you want to build a specific structure like a miniature Eiffel Tower. However, the problem is that the bricks in the box are a mix of various shapes, sizes, and colors, and they do not exactly match the design of Eiffel Tower. What's the solution? Find the right bricks, add them to your Lego box, and build your Eiffel Tower. Similarly, in machine learning, specifically LLMs are pre-trained on large amount of data, such as summarization, question answers, and many other. And when you try to ask a very specific question like, hey, what's the profit of Tesla this year? There might be a chance that model is not pre-trained on that latest dataset. So what's the solution then? That's where fine-tuning comes in, where we introduce new dataset to the original model. We make a copy of this model and then using these learned weight as a starting point, we retrain the model on a new domain-specific dataset so that it can answer our specific questions. For the fine-tuning, we first have to identify the task and gather all the relevant dataset. Then we will pre-process the dataset according to the requirement of model. We will initialize the model and then we will fine-tune the model with our specific dataset. Lastly, we will evaluate the result of that particular model. Determining the best technique is still an ongoing area of research and may depend upon your requirement. But recently, one of the most effective technique is PEFT, parameter efficient fine-tuning, because of its cost, time, and response efficiency. Moreover, PEFT is prone to catastrophic forgetting, which means it can still remember its previous data even after fine-tuning. In this video, we will discuss about low-rank adaptation of large language models, or simply LoRA, where LoRA approximates the model's weight matrices with the low-rank matrices. This reduces the number of parameters that need to be fine-tuned and hence makes the fine-tuning really fast and efficient. As you can see in the screen, for the LoRA, each weight is represented by 32 bits. That means for a 7 billion model, we need 28 gigabytes of GPU to run that model. While there is an upgraded version of LoRA, that's quantized LoRA or QLoRA, where each weight is represented by 4 bits. That means for a 7 billion model, we only need 3.5 gigabytes of GPU to run it. And that's it for today's fine-tuning. If you want to know more about fine-tuning and how Royal Cyber is using it to create cutting-edge solutions, feel free to contact us at info@royalcyber.com.